So in part of the lectures on spectroscopy for the advanced experimental techniques, I wanted to go and give some examples of some real world experimental examples, both things that we use in the lab and also large science experiments. And then we'll finish by discussing some of the spectroscopy or applications of spectroscopy that don't use light as the stimulus, but go beyond light. So again, just to recap, the features we're looking for in a spectroscopy experiment is a stimulus source, a radiation source, some optics, our sample, then some detector optics that do things like, for example, spread out the different wavelengths or frequencies we're seeing, or do some filtering, and then the detector. Okay, so a first example is going to be of a Raman spectroscopy system. So this is a technique which could be used to look at the vibrational modes of individual molecules. So if you take, for example, the water molecule, then it has various modes in which it can vibrate. So there are some modes which involve the two hydrogens moving in and out in phase, and then there are versions which involve them moving exactly out of phase. So that's another mode of vibration. And then you've got various bending modes as well, as the hydrogen bonds stretch up and down. And each of those vibration modes has some kind of characteristic energy and some kind of characteristic frequency. So what we're going to try and do is use a spectroscopy method to actually analyze those individual modes. So what we're looking for here is modes which are going to be optically active. And just as we talked about when we talked about lasers and stimulated light emission, we're looking for processes where whatever's going on in the sample we're looking at is going to couple to light. And that means we have to have some kind of dipole involved. So Raman techniques only work where the vibration mode you're looking at has a dipole that changes. So those are the only things which are said to be Raman active. So what happens in this situation is we put in some light of some wavelength, and that potentially excites the molecule up to some very high energy state. And normally those states we get into, they don't correspond to any particular energy level of the mode we're trying to excite. There's some superposition of lots of very high energy states. And because of that, they're relatively short-lived. So then there are two things that might happen. The first thing that might happen is that virtually excited state might simply just collapse straight back down to our ground state. And that will emit a photon of the same energy as was absorbed in the first place. And so this is a process known as Rayleigh scattering. So that's where there is no change in the energy of the photon. You put photon in, you get a photon out, and nothing particularly exciting has happened. However, if you have a lower lying excited energy state, which has this ability to have this transition dipole associated with it, then as you go into the virtual state, what can happen is it can collapse back down to the excited state. So if you go from the ground state, you go up to the virtual state, and then you collapse to the excited state, and then a short time after that, it's going to collapse on down, back down to the ground state. And because there's a dipole, transition dipole associated with going from the excited state to the ground state, as it goes back from the excited state to the ground state, it's going to emit a photon. But that photon it's emitting is not the same energy as the photon you put in, because the photon you put in went from the ground state to the virtual state. You then got quickly from the virtual state to the excited state without emitting a photon. And then you go from the excited state back to the ground state. But that process going from the excited state to the ground state does then emit a photon. And so what happens is you put photon in, but the photon you get back is at a slightly lower energy. And that is a process called Stokes scattering. And then it turns out there's an equivalent mechanism. If you start in the excited state and then you excite up to the virtual state, you can then collapse back down to the ground state, and that process emits a photon. Only in that case, you absorbed a photon of one energy and you got back a photon of a bigger energy. And so that's called an anti-Stokes mechanism. Now, in real systems, Stokes mechanisms are more common than anti-Stokes, because in most real systems, you start in the ground state. It's only if you actually manage somehow to start in the excited state and not in the ground state that you're going to see the anti-Stokes mechanisms. So mostly what we look for is the Stokes mechanism. So we look for a reduction in the energy of the photon that's coming back out of our system. But as I say, the key thing here is that you have to appreciate is you have to have a dipole that changes as you go from the different states. And so that puts constraints on both the symmetry of the molecule or the material you're looking at, and also whether or not you generate a dipole as you go from state to state. You don't have to have a dipole before you started necessarily, although as it happens, water does, because as we saw with the previous discussion about lasers, in fact, just the time evolution from one state to another state may be enough to give you that transient dipole. Okay, so this is how it actually looks in practice. This is sort of a rough schematic, as it turns out, of the Raman microscope in the condensed matter labs. So we start on the left there, we have lasers, and our system has 3 lasers. So we've got a blue laser, a green laser, and a red laser. And you can choose different lasers for looking at different materials. And that's to do with how easily it is to access the virtual state, the virtually excited state. So that laser passes through a beam splitter, is then taken through essentially a microscope. So it goes through some microscope optics, so you can focus the beam onto a spot on your sample, and then it irradiates your sample. And the power of lasers being used is quite high, because these Raman processes are relatively unrare. So you have millions times more Rayleigh scattering going on than you do have Raman scattering. So much more elastic scattering than inelastic scattering. And that itself is sometimes a problem, because you're going to end up burning your sample through the amount of light you're shining on it. So then most of the light that comes back, so 999,999 parts in a million, is at the same wavelength that you put in. But there is a very small part coming back that is at a slightly shifted wavelength. And in Raman spectroscopy, we tend to talk not so much about the shift in wavelength, but we talk about the shift in frequency. And we don't express the frequency in hertz, because it turns out that expressing the numbers in 1/centimeters, inverse centimeters, or wave numbers, it's historically what it's done, but the advantage is it gives you numbers that are a bit easier to work with, rather than dealing with frequencies at sort of 10 to the 15 hertz. What we typically see is that there is a shift in the frequency coming back, which is somewhere between 50 and a couple of thousand wave numbers. And so that represents a relatively small shift in the frequency, but it's enough to be detectable. So we send that back up through the system, goes through the beam splitter, and we're interested in looking at the part that goes straight the way through. So note the way we've arranged the beam splitter here, the only peak coming back is the Raman scattered stuff and the Rayleigh scattered stuff. We don't ever see the incident laser spot directly. That is then, it goes through a series of focusing optics, but is then shone onto a grating. And then that grating causes the different wavelengths of the light in the signal to be spread out. And so what we see is essentially a diffraction pattern of that grating. So obviously in a diffraction pattern, just thinking about, say, young slits experiments, this is essentially the same concept. The spacing between your bright fringes you get, the bright spots, depends on the wavelength. So different wavelengths are going to appear with different spacings of spots. So the straight through beam, what's called the 0-0 peak, well, that doesn't depend on the wavelength. That just gets all the light coming through. So that's the not diffracted spot. And then on either side of that, you get the first order diffraction spots. But on that diffraction spot, you get a very, very bright spot, which is the Rayleigh scattered light. And then on either side of it, you get the Stokes and the anti-Stokes. signal. And so because you are now looking at things which have shifted in frequency, they're being separated out. And then the final thing you have to go and do is have a very, very good notch filter. And that can be as simple as just a plate you're moving across the diffraction spot, across the diffraction pattern, that cuts out the very, very, very intense Rayleigh scattered peak. Because if you let that fall on your detector, then you're going to burn your detector out, or at least put it into a state where it's going to take a long time to recover. And you're trying to spot not the million photons that were Rayleigh scattered, but the one photon that was Raman scattered. And so what you then do is take that diffraction pattern and shine it on a CCD, and simply the pixel that you run on your CCD tells you what wavelength you had, and therefore what the shift in frequency or shift in wavelength that you're seeing relative to the Raman signal. And then if you do that for a whole range of wavelengths, you get a signature of the material you're looking at. So this particular example is looking at, I think it's C60 on silicon from memory, and you've got some peaks there which are to do with the silicon, and then you've also got a variety of other peaks, and these are essentially labeling different vibration modes in the fullerene cage. And what it's doing is it's telling you about the symmetry. So if you've done any space group theory, then this relates to space group theory for the symmetry of vibration modes. And so again, not all vibration modes you see, because they're not all Raman active, but you get this sort of fingerprint of the ones you do see. And from that, you can tell a lot of information about the molecular structure, including, for example, whether it's sitting freely and able to freely move, or whether it's been a bit deformed because it's sitting on some kind of surface. So you can get really a huge amount of information out of this sort of spectroscopy technique. You don't have to supply the radiation yourself in order to go and do a spectroscopy measurement. So if you're dealing with astrophysical sources, then your radiation sources are typically the things you're looking at, unless you're studying things like interstellar clouds, in which case obviously you're essentially doing an absorption experiment, but using the star behind that cloud as your or whatever that the astronomical object behind your cloud of interest is. Again, you can do some really clever and sophisticated experiments. So this is a particular example of a type of spectrometer which not only spreads out the different wavelengths and light in one dimension, but then within that then spreads it out in a perpendicular dimension. So you're actually spreading out the different frequencies of light that you're seeing across the whole 2 dimensions of a detector. And that means you can get some really phenomenal accuracy. And so the particular application here that they're looking for is to look for the redshift that's caused in the spectrum of a sun due to the fact it's wobbling backwards and forwards as some exoplanet is orbiting it. So if we think about our solar system, as the planets in our solar system orbit the sun, I mean, obviously they're not technically orbiting the sun, they're orbiting the center of mass of the solar system. Now, the center of mass of the solar system is within the sun, but it's not actually at the center of the sun. And so what happens is the sun, center of mass of the sun, is also orbiting the center of mass of the solar system, and it is wobbling a little bit relative to an observer far away, and that wobble is being caused by the fact that the planets are dragging it around a little bit. Now that wobble means it's moving. In fact, it's moving means that you've got some level of redshift going on in the star, which changes over time. And this is trying to detect that infinitesimally small redshift wobble that's being caused by having, well, small rocky planets. By that we mean like kind of Earth-sized objects. So this is trying to detect Earth-like planets in orbit around distant stars by seeing how much the wavelength of that star is shifting. And in particular, what you're doing is you're looking for particular emission lines because they're easier to spot. So you're looking for emission lines that are shifting backwards and forwards in the spectrum, rather than trying to spot the shift in the black body radiation. But again, it's a genuine example of where these sort of spectroscopic techniques are sort of doing cutting edge research. And of course, as the astrophysicists will know, if being able to go and switch to look at the galaxy or the night sky in different wavelengths is incredibly useful, because you get different information when you look at different wavelengths. So looking at the Milky Way in the visible, you can see that there's quite a lot of it is obscured by dust clouds, not necessarily letting you look through what's behind them. If you switch to X-ray, then you suddenly start seeing there are different sources there. There are still some things which are obscuring the X-rays, but for example, you can, in this case, pick out a supernova remnant that wasn't there in the visible light so easily to see. And it's kind of a very famous example is if you look at the microwave spectrum, then you get a very different view of the solar system. Now you can see past all those dust clouds. That's to do with the size of the dust particles compared to the wavelength of the light you're using, which is why you can see past it. Also what you end up seeing is you see this texture in the background to the Milky Way. And so what you're picking up here is the cosmic microwave background, and that of course famously is telling you about the structure of the early universe. So again, just simply by using the concept of spectroscopy, by looking at different wavelengths or frequencies in your radiation spectrum, you're able to get additional information that you wouldn't have otherwise got. Closer to home, and certainly closer to my own research area, another example where it's not just changes in energy that you might be looking for, you can also be looking for changes in polarization in a spectroscopy experiment. And so this is a particular example which uses what's called the magneto-optical Kerr effect. So the kind of story behind this is that if you look at a dielectric susceptibility, so this is we apply a electric field to a material, and that electric field causes a displacement current. So this is the D of Maxwell's equations. Then that is related not only to the electric field you apply, but also to the polarization of the material you're looking at. And then in turn, you can describe that polarization as being related to the applied electric field. And the constant of proportionality is the dielectric constant, except that in general, it's not a constant. So in this case, we're describing the polarization as a vector and the electric field as a vector. And then in between those two, joins them up, has to be a tensor. So in fact, that dielectric constant is not a dielectric constant, it's a dielectric tensor. Now, most of the time, we don't worry about the fact of the tensor. But if you actually write it out like this, then what you see is that it's got diagonal terms, which in this case are all the same. That would represent the thing you normally think of as being the dielectric constant. But then you have these off-diagonal terms. And in a magnetic material, it turns out that those off-diagonal terms depend on the magnetization of the material. So what does this mean? What it means, if we start off shining light from a laser, we pass it through a polarizing filter, so it's plane polarized, say horizontally, and it lands into the sample, and then it undergoes a process of reflection. But the process of that reflection involves it interacting with the dielectric constant of the material. But the dielectric constant of the material has these off-axis terms, which means that when the light comes back at you, it's no longer plane polarized, but it's undergone some change in polarization. One of the ways of thinking about what's actually happening here is that we can think of that horizontal polarized light as being one component that is going clockwise and one component that's going anti-clockwise. And then as those clockwise and anti-clockwise components of light propagating, associated with them, because they're a circulating electric field, there's a magnetic field, and that magnetic field is going to be pointing either towards the sample or towards the laser. So then when those two components of light enter the sample, because they've got a magnetic field associated with them, and the magnetic field is pointing in opposite directions for the two components, it has a different interaction with the magnetization of the sample. And as a result, one of those components is retarded, so it's given a phase lag relative to the other one. And so what you have coming out is that the light, when you join those two components that have been reflected back together, they're now slightly out of phase with each other. And so now it's not a nice plain polarized light, it's ever so slightly elliptically polarized. So in other words, the net electric field, the total electric field is not going just left, right, backwards and forwards, but it's going around in an ellipse. And that means that if you then try and pass it through a perpendicularly polarized filter, because it's now elliptically polarized, some of the light will get through. And so what we're able to go and do is measure this change in polarization of the light that's been caused by the effect of the magnetization of the sample. And so that is giving us information about the magnetic state of the sample by measuring the polarization. And in fact, you can do a similar experiment and you do it in transmission if your sample is transparent, in which case you're looking at the Faraday effect. But it's the same basic idea, that is to do with the fact that the dielectric constant of the material is in fact a tensor, and it has terms, then off-diagonal terms, that in that tensor that depend on the magnetization of your sample. Okay, so we've talked so far primarily about doing spectroscopy with light. So just to finish with, I want to give some examples where we do spectroscopy with things that aren't photons. Okay, so just as a review where we've got to, we've got photons, which we've been discussing mainly. So those are zero mass, integer spin, zero charge particles. But they're not the only particles we could be using. So we could think about trying to say, could we do this with an electron or a proton? So now we have a non-zero mass particle, and it's a fermion, it's a half spin, and it also has a charge. Now electrons and protons are both nice stable particles, so that's okay. But we don't have to do that. We can pick pretty much any particle we want from the standard model. And one of the ones we use ourselves in our research in Leeds is we make use of muon spectroscopy. Now, we don't have a muon source in Leeds. We have to go to the Paul Scherrer Institute in Switzerland, where they do have a muon source. And the reason we like using muons is that they are heavy, significantly heavier than an electron. They also have a half spin, and they can also have either plus or minus charges, depending whether it's a muon or an anti-muon. But they're not stable. So a muon will last for about 2.2 microseconds on average. So you have this sort of megahertz timescale decay process going on. And that turns out to be rather useful. So let's start off with the simple particles first. So electrons. And in fact, an electron spectroscopy experiment is dead simple to do because it's what's going on in your electron microscopes. So just as we were talking about doing diffraction experiments with X-rays and using the scattering of X-rays, an electron microscope is doing a scattering experiment with the electrons, as you're using the wave-like nature of the electrons to go and do a diffraction experiment. So you start off with an electron gun of some sort. Usually these days they're field emission guns. You then have to have lenses to focus. Well, you have to have some way of extracting the electrons from the source and accelerating them out very fast. You then have to have some kind of focusing. In an electron microscope, we primarily use electromagnetic lenses to do that focusing. You then end up going through your sample. You then have more lenses at the back of it. And you've got two options. You can either project the diffraction pattern you've got onto the viewing screen, which can be as simple as a fluorescent screen. Again, most microscopes these days use CCDs to go and detect the scattered electrons, but you can also do it with just a simple fluorescent screen. My final year project, I was doing electron microscopy, and literally I was looking at a phosphor-coated plate through a glass window on this microscope, and that is how I observed the electron microscopes. I have to say it was a very elderly electron microscope even when I did my bachelor's degree in 1991, so 1991, 1994 even. But these days typically you use some sort of CCD system and get huge amounts of data off that way. Because the electrons are massive particles, as in they have mass, their wavelengths you can get just through de Broglie is very, very short. So it's easy to get electrons whose wavelengths are much, much shorter, even than the scale of an atom. You do have to be a bit careful because you can eventually get to the point where you have to think about relativistic correction. So if you accelerate electrons by 100 kilo electron volts, you have to start thinking about making relativistic corrections to work out their wavelength. So that then means you can go and look at the diffraction pattern from a crystal structure. And in fact, the example that's been given here, if you look at it carefully, you'll realize that it's got five-fold symmetry. And that's kind of unusual because you can't really make a repeating structure that has five-fold symmetry. In other words, you can't tessellate pentagons, you can't tessellate pentagons so that they repeat with all the pentagons in the same orientation. So if you pick your pentagonal pattern up, you can't rotate it round by a fifth of rotation and also be able to translate it freely. So in fact, there's relatively few patterns which you can show five-fold rotation, and they always have a single point of five-fold rotational symmetry in them. And the most classic example of that is a Penrose tiling. And the real material which shows symmetries are a class of materials called quasicrystals. And quasicrystals are interesting because they caused the International Crystallography Union to have to redefine what a crystal was. So they originally defined a crystal as being something which had translational symmetry and rotational symmetry, meaning you could pick it up and move it around and land it back on a lattice and it would look the same, and you could spin it round through some angle and it would look the same. But a quasicrystal you can't translate. But it still shows diffraction. And so why is that? And the answer to that question is that although in 2 dimensions or 3 dimensions, it's not a periodic structure, it doesn't translate. If you take it into a higher number of dimensions, then it does become a periodic structure. So again, the classic example of the Penrose, in fact, turns out to be a 2-dimensional projection of a 5-dimensional cubic structure. And because it's a 5-dimensional cubic structure, it can diffract, even though it doesn't repeat in 2 dimensions. So that's kind of weird and wacky. Anyway, that's about quasicrystals rather than electron spectroscopy. So as well as doing the electron diffraction, the other thing you can do is you can look at the energy of the electrons as they're passed through the sample. This is a technique called EELS for energy electron loss spectroscopy. And what you're looking at is the electrons having given some of their energy away to the material, to its bonding structure. And so you can fingerprint different bonding types within the material. If you use much higher energy electrons, look at much higher energy losses of electrons, then those electrons can also knock electrons out of core shells, promote them to high energy. And just as we saw with the X-ray tube source, they can result in the production of X-ray photons that are characteristic of the elements that are present. So the other source of spectroscopy we typically do in an electron microscope is to look at the emitted X-rays from the sample caused by the electrons hitting it. And that can give us information about the elements, the elemental analysis, the chemistry. And so with a sophisticated electron microscope, you can, particularly one where you can focus the beam down to a very, very fine spot and then scan it over your sample, looking at the X-rays that have been given off as you move around, you can actually build an element map that shows you exactly where the elements are within your sample. Okay, and then I said the other example that particularly we're fond of is looking at muon spectroscopy. And so what happens here is that you take your muon and you fire it into your sample. If your sample is magnetic, then there's a magnetic field present, and the muon will precess because the muon has a spin. And so the muon will, on average, precess around about that magnetic field. Now, if you start your muons all lined up with their spins all lined up together, then as they fly through the sample, they'll all precess, and the rate at which they precess will tell you about the local magnetic field. So at some time later, the muon will be pointing in some direction that's different from the direction it was originally pointing in, because it's precessed around the local magnetic field. But as we said, muons don't hang around forever. They'll only last 2.2 microseconds, which means that at that point, eventually it'll undergo a spontaneous decay. And as part of its decay processes, it'll release some positrons. And it turns out the positrons are easy to detect. And so what we go and do is we simply have two sets of detectors on either side of our sample, and we look at the number of positrons being collected on one side versus the number of positrons being collected on the other side. And that in turn tells us which way the muon was pointing at the point at which we decayed. And so we know when we put the muons in, they go in with a little burst, they go in one at a time, and then we wait till it's decayed, we see where it went, we say, okay, it was pointing to the left or it was pointing to the right when it decayed, and we know how long it was before it decayed. And so over time we can build up a histogram of which way the muon was pointing as a function of time. And that in turn is telling us then about the rate at which it's precessing, which in turn is telling us which way the magnetic field was pointing. And although that sounds a horribly convoluted way of measuring which way the magnetic field inside the sample was pointing, it in fact turns out to be the world's most sensitive magnetometer. And so we're able to measure smaller magnetic fields deep inside a sample than with any other technique at all available to us. And so this can lead to some really startling discoveries about what's going on in your materials. And so our kind of most famous example of this is when Dr. Cespedes and his PhD students and an MPhil student realized that at the interface between C60 and copper, that interface became magnetic, even though neither C60 nor copper are magnetic. And so we actually were able to show that was what was going on, partly through this muon experiment, because we could control where we stopped the muons. So we had different amounts of gold on top of the sample, so the muons would travel a different distance into the sample on average, and then watch what the local magnetic field was, and showed that there was a magnetic field associated with that surface. So that's a rather nice example of a spectroscopy application where there's no light involved at all. Another example, in this case of an interferometer, very famous current example is the LIGO experiment. So this is trying to detect gravitational waves. And basically this is an interferometer where we fire light up two perpendicular arms, which are massively long. And what we're looking for is a change in the length of those two arms. So it's set up that sort of in its rest state, those two pulses of light will will interfere with each other, say in constructive interference. If we then repeat the experiment as a gravity wave passes through, then what happens is the path difference along those two arms becomes different. And so where it was in phase to start with, it ends up being out of phase. And so that's the dead simple basis of the experiment. But as has been in the physics news from a couple of years ago or a year ago, it has successfully detected the presence of gravitational waves propagating across the galaxy. And so, you know, again, an interferometer based on the Earth can tell you something about what's going away across the other side of the galaxy. So that's then the end of these sets of lectures on spectroscopy. So it's really a dead simple technique at its heart, and it's really very, very powerful. And there's this huge range of techniques and a huge range of options. So which is one of the reasons it's so powerful, because you can always measure pretty much any parameter you want to go and measure with some kind of spectroscopy technique. And it's just so broadly applicable from all forms of radiation. Doesn't just have to be electromagnetism, it can be anything you want. And so you end up with new discoveries just coming by, not quite every day, but every some short time period.